Good morning, ladies and gentlemen. Welcome to another PMC online pre-training session. Today, as you all aware, that we started last week talking about reboilers. So to finish off this module, so we're going to talk about condensers for today. And as you know, you can stop us anytime that you will have a question or you need further clarification, because obviously all those topics are new to hear about in terms of the details. And I think it's a good opportunity for you to refresh your information with respect to reboilers. So stop us anytime you have questions to clarify. I'm going to hand over to Olga, and all of you, I guess you know Olga now. So she will take us through the slides for today. Thanks, Olga. You can take over. Thanks.
Hey, hello. Thank you, Ahmed. Hello, everybody, and welcome to this second session of Reboilers and Condensers, where today we are going to talk about condensers. We are gonna start talking about condensing phenomenon. Then we are gonna have a short introduction to condensers. And right after, we will see all different type of condensers. And we will finish with some parameters that we have to consider to select the right condenser design. And at the end of the presentation, we will talk about two different exchanges, one reboiler and one condenser you have in the Garbala refinery. So first, what is condensing? Condensation is the change of the physical state from the gas phase into the liquid phase. Often, the vapor entering in a condenser is superheated, as you can see in this graph, where we have the enthalpy and the temperature. We have the fluid that we want to condense. It enters a bit superheated, which means the vapor is at temperature greater than its dew point. Then this fluid is being condensed, and right after we have some subcooling that prevents flushing in the condensate discharge system, which causes problems if the condensate is pumped. So if we have a pump right after our condenser, it is good to have some subcooling to ensure that we will not have a phase separation or some vapor at the pump inlet. So condensers are responsible for removing heat from vapor so it can be converted to liquid. Usually condensers are located at the outlet of the top of a distillation column, as you can see here in the sketch. We have the column and here the condenser, where the vapor leaving the top of the column is cooled and condensed in this device. Condensing fluids are usually cooling water or air, depending on the distillate temperature and other factors. Okay. And well, there are a wide variety of condenser types to be chosen according to its service. This is a wide graph where you can see all different condensers we can have in the industry. We can have the water-cooled condenser with double tube or double tube condensers. We can have also shell and coil condensers, also the shell and tube condensers. split into internal condensers and external condensers. We also have evaporative condenser, air-cooled condenser, where we can have induced and forced, natural, or A-frame. Actually, all of these exchanges we already talked in our first session regarding the heat exchangers online session. So now we will talk about air-cooled condensers and shell and tube condensers because these are the most common condensers in industry. We're gonna start first with air-cooled condensers, and right after we will talk about the shell and tube condensers. But if you have any question up to now, please just let me know.
No, I don't think so. There is any question so far, yeah.
Okay. So air coolers are often used for condensing services. We already have talked about air coolers, as I said, in the heat exchangers presentation on the first online session we did. I think it was the second online session we did, because in the first one we talked about shell and tube exchangers, and in the second one we talked about air coolers. So we already know the different type of coolers we can find in the industry. Forced, induced, natural draft, and the main parts of an air cooler. In this case, we talk again because air coolers are often very, very used for condensing services in the industry. And they have the particularity that for all condensing services, according to API 661, the last pass of tubes in multi-pass condensers shall be sloped downward at least 10 millimeters per meter towards the outlet header in order to help gravity flow. We have to take special care for subcooling. When a single tube bundle for both condensing and subcooling process is used, usually there will be associated problems because the amount of desired subcooling cannot be guaranteed. There is a rule of thumb that usually when less than 5% of the total duty is subcooled, condensing and subcooling can be designed in the same bundle. But if this value is exceeded, 2 air coolers will be needed, one for condensing and one for subcooling.
Just a minute, Olga. I think we've got a question here.
Yes.
تفضل استاذ عبد الرضا سالت اول الصور. تفضل استاذ.
السلام عليكم استاذ. بس شو يقصد بهاي الكاميرا 10 ملم على متر؟
هذه يقصد بها انت مو عندك اير كولر يعني يصير بها انحدار مقداره 10 ملم لكل متر، يعني اذا هي 10 متر طولها فيصير عندك تقريبا 10 سنتيم بها انحدار باتجاه الاوتلت، يعني سلوبت.
يعني بايوغرافيتي يعني يقصد به يعني شغلات.
لا هسه انت مو عندك اير كولر مثبته
صح،
تشوفها بشكل هوريزونتال، تشوفها بشكل افقي صح؟
تمام. اي
هذا الافقي مو ثابت، يعني بجهه الاوتلت تصير بها نازله، يعني كانما بها انحراف باتجاه الاوتلت.
يعني هاي نسبه اللي دا يقول بها.
اي يعني انت كل متره، كل طول متره تنزل 10 ملم.
واضح.
عفوا استاذ، يعني يقصد ميلان
بالضبط بالضبط بالميلان بالضبط.
اشتي لك استاذ.
اوكي. 6 سراب اتصور اذا تعرف الاسم صحيح. فاضل 6 سراب. اوكي شباب، واحد عنده سؤال او استفسار؟
السلام عليكم استاذ احمد.
السلام ورحمه الله. استاذ مرتضى اهلا وسهلا.
استاذ احمد، بس اذا ممكن مداخله بخصوص التو اير كولر بحاله يعني بنحتاج سب كولينج، يعني ممكن هذا يكون هو سبب انه الاي بي اي يعتبر المحاضره السابقه مال الاير كولر تحتاج 2 فان مينيموم.
ها شلون؟ العفو ما افتهمت.
اكو المحاضره السابقه مال الهيت
اي اتذكر منيو هذاك ديزاين يعني كتصاميم
ديزاين. اي هسه هنا نحتاج انا اسوي كوندنسيت وسب كولينج بنفس الباندل حتى اضمن انه يصير عندي سب كولينج، لذلك انا احتاج تو فان، يعني حتى الفان الاولى تسوي كوندنسنج والفان الثاني تسوي لي سب كولينج.
لا، والكوندنسنج هي البروسيس كلها كوندنسنج. هذا السب كولينج هذا الحاله يعني الفيس تشينج مال الفلويد ما له علاقه. انت مفهوم المفهوم الكوندنسنج هو كله كوندنسنج. جزء هسه السؤال انه الفيس انت شنو هو، منين جاي لوين رايح من ناحيه الفلويد. فاذا هو في حاله السب كولينج هذا سب كولينج، بس كعمليه اوفرول هي كلها كوندنسنج. يعني ماكو شيء، ماكو فقره اسمها اسوي هسه كوندنسنج وبعدين اسوي سب كولينج. لا، الكوندنسنج هي كل العمليه اللي تصير هو كوندنسنج. تفهم قصدي؟
وياك اي نعم.
ما لها علاقه، يعني مو تسوي بروسيس كوندنسنج وبعدين تسوي اكو بروسيس اسمها سب كولينج. لا
لا هو يعني هي حاله اول مره هو مو يصير عندي يتكثف، بس ممكن يتكثف بدرجه الغليان، بعدين انا حتى اضمن انه كله يكون
اي بس انا دا قصده انه الكوندنسنج التكثيف هي كل العمليه بغض النظر عن انت بيا فيس مال الفلويد، هي اسمها كوندنسنج. هسه هاي انتهينا منها، هي العمليه اسمها كوندنسنج. هسه انت تريد تجي تسال تقول انا بيا فيس بيا طور داخل انا الفلويد، هذا موضوع ثاني ما له علاقه، بس هي كلها كوندنسنج العمليه. هذا قصدي.
وياك صح.
اي لا يعني اقصد احنا بدنا نحكي كوندنسنج. هسه تفاصيل الكوندنسنج انت تجي مثل ما قلت انت جاي من فيبر تحوله تو فيس، التو فيس اذا هو ساتوريتد تسوي سب كولينج الى اخره. بس هي العمليه الاصل هي كلها كوندنسنج. اوكي
شكرا.
هلا وسهلا. شباب، واحد عنده سؤال او استفسار؟ Okay, Olga, I think you can carry on.
Okay, thank you. So also, in air-cooled condensers, inert accumulations shall be considered when designing an air-cooler condenser, since nearly all condensers have a small concentration of non-condensable contaminants that can reduce the condenser efficiency. Here in the sketch, we can see how we have our fluid we want to condensate, the inlet in this part. We pass through the tube, all the tube, and here we have a nozzle to take out the non-condensables. And here on the top, on the bottom of the air cooler, we have the condensate outlet. When inert accumulation is an issue, usually a single tube draw design is considered. However, the unit usually costs more than the less effective multi-row design. It's like in this case, we only have one single tube row, just only one pass. So that's all for air coolers. I'm anticipating that at the end of the presentation, the example of a condenser will be an air cooler. So you will see what we talked here in this first slide. You will see the sketch of how this slope it is drawn in the mechanical drawing. So you will see the example of an air cooler. Right now, we will pass through the shell and tube condensers. As we saw on the first classification, we have internal condensers and external condensers, and they are extensively used in the process industries, typically to condense the overhead vapor from a distillation column. For internal condensers, we will see the reflux condensers. And then for the external condensers, there are different type of condensers according to the thema type. So we have the E type, the J type, and the X type. Sorry, just a moment because someone is entering into the
just
room.
go.
So just a moment.
Yeah, sure.
External condensers, we have some different external condensers according to the thema type, the E type, the G type, and the X type. And according to its configuration, we can have them horizontal, shell side, tube side, also condenser. We can have a different horizontal and vertical configurations. And we have also the reflux condenser as vertical and horizontal. And now we are gonna see all these types of condensers and the advantages, the disadvantages, and the main use. So most large condensers in the process industry are oriented horizontally in order to minimize the cost of support structures and also facilitate maintenance operations, because with horizontal exchangers, as we can see, it is easy to take out, to pull out the tube bundle for cleaning operations. So the condensing vapor is often an organic compound or mixture, and the coolant is most often water. Therefore, the condensing vapor is most frequently placed in the shell, and the cooling water, which is usually more prone to fouling, flows in the tubes. So here we are seeing the external condensers, thema E type, that is very, very commonly used. So the baffled E condenser is widely used and the least expensive type of horizontal condenser. As you can see here in the picture, we have the vapor in, which condenses through the shell side, and the coolant on the tube side. We can have a floating head or fixed tube sheet, and the baffles are usually vertical cut for side-to-side flow to facilitate the condensate draining. Also, an extra nozzle at the top of the shell is placed to facilitate the condensate drain, to facilitate the vapor, the non-condensable vent Otherwise, if we do not take them out, they will limit the performance of the unit. So it is always needed to take out all the non-condensable vapors from the shell and tube, from the condensers. And also here in the inlet, an impeachment protection, as we saw on the first session of shell and tube. An impeachment protection is required as vapor enters to the shell site. The best applications of these kind of condensers are when horizontal orientation is required, and also when high pressure or falling requires coolant on the shell, on the tube side. So when, in this case, if we have cooling water, we prefer to place, as we already talked, on the tube side instead of the shell side, because cooling water is a very full fluid. So we prefer to have it on inside the tubes. The advantages we have is that our simple construction and also relatively low cost. And the main disadvantages are that the condensate fluiding with undersized outlet nozzle, it means having this horizontal condenser, we need to have here a sufficient nozzle diameter to be able to take out all the condensate without flooding the nozzle. Also, another disadvantage is possible non-condensable accumulation. It means that we also have to design the correct nozzle size to have good evacuations of the non-condensables. So this is tema E, with the condensing taking place on the shell side. Now, we are gonna have also the tema E type, horizontal, but where the condensation takes place on the tube side instead of the shell side. This configuration is sometimes used to condense high pressure or corrosive vapors. So the best applications are when the condensing fluid needs to be located in tube side due to its nature as corrosion, high pressure fluids, or very, very full vapors. So we place the vapor in the tube part, and inside the tubes is condensed. In this case, the coolant would be placed on the shell side. And we will have in the tube side part the same. The condensed on the bottom of the condenser. And also we will place a nozzle to evacuate the non-condensables. The advantages of these condensers are that horizontal orientation sometimes preferable to vertical due to shell type or construction limitation. And also there is good heat transfer rate when flow velocity is high. The main disadvantages are the possible non-condensable accumulation. As I said, we have to place here a good nozzle with a good diameter to evacuate the non-condensables. So we have talked about the horizontal condensers. Now we will see the Tema E type with vertical shell side condenser, which means the vapor is entering into the shell side where it condenses, and in this case we'll can say the coolant, maybe cooling water. We place the cooling water on the tube side to condense the shell side fluid. So we have the vapor in the top of the vertical condenser. It passes through the tube bundle and the baffles, where it condenses at the condensates go out at the bottom of the exchanger. Here we also have the condenser's outlet at the bottom, and also a vent for the non-condensables. We need also for the tube side part to have a startup vent on the tube side part, also on the shell side. So the best applications of this type of exchangers are when boiling coolant applications are required. And the main advantage is the good drainage and also the relatively high heat transfer coefficient due to disruption of condensate film boiled up by baffles, which means that since we have here baffles, the heat transfer, the velocity we have on the shell side is high enough, and also this move of the fluid makes that facilitates the separation between the liquid and the vapor. And finally, the main disadvantages are that the tube side mechanical cleaning may be more difficult because it is difficult to take out the tube bundle because sometimes there is not enough space to below the exchanger to pull out the bundle. And also the structures are more expensive, the support structures. And we have also the vertical exchanger where the condensing is taking place inside the tubes. It consists of an shell with either a floating or fixed tube sheet. The lower head is oversized to accommodate the condensate and the vent for non-condensables. And the upper tube sheet is also provided with a vent to prevent any condensable gas, such as air, that may enter with the coolant from accumulating in the space between the tube sheet and the upper coolant nozzle. The condensate, we have the vapor entering into the tubes at the up of the exchanger, which goes into the tubes, and the condensate flows down the tubes in the form of annular film of liquid, as you can see here. If we zoom the inside of one tube, we have a film of these where the vapor flows in the middle, and there is a film of liquid at the walls of the tube. So thereby, we maintain good contact with both cooling surface and remaining vapor. So when this vapor gets condensed, we have the condensate out at the bottom of the exchanger, and we have a small, like with a baffle in this part and with a nozzle to be able to take out the non-condensable gas vapors. So the best applications are when shell site maintenance or mechanical considerations are not factors, and also when applications that require subcooling or involve wide condensing range mixtures. The main advantage is the good annular contact between condensate and cooling surface, the excellent subcooling characteristics, and also removal of non-condensables with condensing fluid is very easy. And the disadvantages are that the shell site cleaning may be more difficult if shell site fluid falls. So we have finished the E-type external condensers. If you have any question up to now, please just let me know.
Guys, do you have any questions so far? Yes, Mustafa, Mr. Mustafa.
السلام عليكم استاذ.
السلام ورحمة الله.
استاذ بس اكو احتماليه انه يخرج الفيبر ويا النون كوندنسبل فنت، واذا اكو هيك احتماليه شنو الحل اللي نقدر نسويه حتى نضمن انه ما يخرج؟
Olga, the question is about the non-condensable vent. So is it gonna happen anyways that always you're gonna have non-condensable vent, or like you cannot condense some of the vapor, so you have to have a vent to obviously maybe avoid pressurization, or so if you just give some details on the non-condensable vent, please.
Yes, this vent is, if you take a look to all condensers in industry, you will see that 99.9% of the condensers have a vent that allows to take out the non-condensables. There is always, like as I said, 99.9% that we have non-condensable vapors. So we need to take them out, otherwise they will remain inside the shell and tube, inside the heat exchanger. And having non-condensables in the heat exchanger is not good for the thermal performance because it decreases the heat transfer coefficient.
Sure, yeah.
So it decreases the performance of the exchanger. So it's very important we take them out to ensure a good function of the exchanger.
Thank you, Olga. Thanks. أستاذ مصطفى، ما أعرف واضح الجواب لو أعيده؟
استاذ هو واضح الجواب.
يعني هو أنت ما عندك efficiency 100%، فلازم عندك non-condensable، فأنت حتى تخلص
يعني عادي يطلع فيبر ويا النون كوندنسبل.
اي هو شنو النون؟ انت داخل عندك فيبر، شو تريد تسوي؟ تريد تبرده وتسوي لك
استاذ احمد، بس اعتقد سؤال انه هو كان يعني قصده شلون ما يخرج الفيبر ويا الكوندنسيت من جوا، يعني شنو الطريقه اللي راح تمنع الاختلاط بين المي والبخار بالخارج مع الكوندنسيت؟
مو البخار الفيبر دائما يسلك الطريق الاسهل، فهناك عندك تو فيس بالخارج، فالإعاقة أعلى، فوين يروح يختار الباث الأسهل، فيروح باتجاه النون كوندنسبل بند. واضح؟
واضح.
بس هو لازم موجود، يعني you cannot avoid it، يعني ماكو طريقة أنت أكو طريقة يصير عندك كله سائل، ماكو هيك شيء يعني. لازم عندك نون كوندنسبل، فشي يسوي له؟ يسوي له venting. Okay. Any more questions guys؟
لا استاذ، بس السلايد اللي قبله.
Olga, can we go back please to slide 41? اي استاذ تفضل.
استاذ هاي الستارت اب فينت هذا يعني هو ذاكر هنا وين بويلينج كونتاكت، يعني هذا شلون نلقاهن بالتوربينات مال البخار الضغط العالي، يعني نفس الشيء يعني شلون مثل ما تقول حتى لا يصير هامرنج ببدايه التشغيل، هذين الفينتات usually closed.
Olga, could you explain please about the startup vent usually closed? So what happens in the startup and why we need them?
Well, it depends how the plant is, how the part is gonna be started up. There are different operating methodologies, but usually in the startup, as I said, it depends on the philosophy of the company, but for the startup,
yeah,
it depends. We can start exchanger before just entering the coolant part on the shell side,
yeah,
or the vapor in the tube side. Usually for condensers, we start just the first part we start up is the part where the cooling water is placed. So in this case, vertical shell side, we will start the condenser with the tube side, with the cooling water on the tube side.
yeah.
And this nozzle will be open just to remove all what we have in the shell side part, and then we will enter the vapor to start condensing. But this nozzle, when we do the startup, after the startup, we will remain closed.
Yeah.
Since we have already here the vent,
yeah,
and we won't need this anymore.
Okay, so it's only during the startup. Yeah.
Yes.
Yeah,
same as for the tube side. When we start entering the cooling water, we will have this opened, but then it will remain closed. It's just to
dispense any vapor inside the tubes or
exactly
the startup.
Yes.
Yeah. Because usually maybe they were under preservation or whatever.
Exactly.
Okay. استاذ ما اعرف اذا واضح الجواب.
استاذ اوكي واضح، بس يعني هسه هذا اليوجوال كلوز فينت ليش ما شفناها بالبقيه؟ هسه انا فهمت الفكره.
لا هذا مثال، بس هن كلهن يكون
موجودات بالبقيه هم.
بلي انتم دائما من تشوفون فد رسمه او فد شيء، هذه مو رسمه تفصيليه يعني، بس هي تعطيك افكار عن شنو اللي انت تشوفه يعني.
اوكي واضح.
هو شنو حتى اخاف عندك نيتروجين باقي بيها بريزرفيشن قبل ما تشغل، فانت تفتح هذا الفنت حتى اذا السائل يجي يملي الحيز، ما تريد غاز داخل الانابيب او هواء داخل، فكله طرده حتى تزيد عمليه الهيت ترانسفير.
واضح.
اوكي.
منونك رحمه الله.
Any more questions شباب؟
العفو استاذ احمد، مداخله بسيطه بخصوص هذا الفنت.
نعم.
يعني مو انا اذا الفائده من هذا الفيرتيكال شيل سايد كوندنسر هو حتى اوصل الكولنت لمرحله الغليان، فاني اضطر بدايه التشغيل غلقه يعني الفنت، مو هيك يعني
شلون
يعني هو
يعرفوا ما
يعني العفو البيست ابلكيشن لهذا الكوندنسر هو انه اوصل عندما احتاج الكولنت مالتي اوصله لدرجه الغليان.
ليش يعني المي الراجع هسه عندنا بالمصفى تغلي يا من يرجع؟
هو هسه المكتوب عنده يقول لك يعني وين boiling coolant application are required، يعني انه يكون مو بس اني اكثف، بس بنفس الوقت احتاج اسوي بويلنج للكولنت.
بلي اي ما تاخذ على الكولد ووتر. اوكي بيست ابلكيشن. اوكي زين شنو السؤال؟
سؤال يعني هنا انا لذلك انا اضطر اغلقه حتى يعني يوصل مرحله الغليان هذا الكولنت.
احنا هسه عندنا نحكي على ستارت اب فنت صح؟
ايه تمام ايه.
هذا بس هذا بس انت يعني ميز بين المراحل التشغيل. انت اول ما تشغل تدخل الكوندنسر بحيز العمل، انت شو تسوي؟ ذن الفنتات تكون مفتوحه. ليش؟ حتى اخاف عندك غازات بداخل الشل او التيوبس. انت شو تسوي؟ انت اول شيء تتعامل ويا سائل بالبدايه، باعتبار انت بعد هذه المرحله مو راسا تبدي عندك توصل مرحله الغليان مثل ما قلت. فبالنتيجه شو تسوي؟ ذني الفنتات مفتوحه بس مرحله الستارت اب، تطرد الغازات الموجوده، وراها من بس عندك سائل تسدها ويبدي عمليه التشغيل الطبيعيه. يعني اقصد انه تدخل بمرحله النورمال اوبريشن. نورمال اوبريشن لان يكونن مسدودات، ما لها علاقه بالنورمال اوبريشن انه انت توصل بويلنج لانه هذني مسدودات، لا يعني ماكو ربط بين الموضوعين. لان لغرض انه تطرد الغازات الموجوده. هاي
تمام شكرا استاذ.
هلا وسهلا. احد عنده سؤال او استفسار شباب؟ لو نستمر. Okay, Olga, I think you can carry on. Thanks.
Okay, thank you. I just want to add that for the vertical condensers in industries, usually most common the vertical tube side condenser than the vertical shell side condenser, because in this case the condensate outlet is better placed than in the shell side condenser, where the condense remains here, and we have to have this path very, very well designed to avoid having condensate, too much condensate here. So the evacuation of condensates is better in the vertical tube side condenser, since the nozzle is located at the bottom of the exchanger. So now we are gonna see the J type, thema type. J type as the same as E, but the condensing fluid is on the shell side because we have horizontal shell side condenser. So the thema type in this case is G, which has a difference between E type, that we have two shell side nozzles instead of having only one. So with J type, we have two nozzles at the shell inlet. So in that way, we can split the inlet flow rate into two nozzles, and then the pressure drop and the velocity is lower at the shell side inlet. So in this case, the vapor goes down. Here it is split into two nozzles, and it enters into the shell side, where it flows through the bundle, and it condensates and goes out with this nozzle located in the middle of the shell side, and this side the same. And we have in the middle a full circle partition. Again, in this type of exchanges, we also have accumulation of non-condensables that we have to take them out. So we need to have a vapor nozzle, and the cooling water will be placed here in the tube side. So the best applications are when high pressure or fouling service requires that coolant service is on the tube side, and also for low pressure drop applications, because as I said, we split the fluid into two parts, so then we decrease velocity and we decrease the pressure drop. The main advantages are the simple construction and relatively low cost, and also the lower pressure drop than equivalent to E-shell. And the disadvantages are the condensate flooding with undersized outlet nozzle. So we have to keep in mind that we do not want flooding nozzle. So this nozzle will be designed with sufficient diameter to avoid having flooding here. And
Sorry,
also
wasn't clear.
yes.
What's the design? The nozzle? Say it again. The word.
Yes. We sometimes in industry, what we have found is that some customers, they say that they have liquid accumulation in the exchanger. Okay. And sometimes this is due to have an under-designed outlet nozzle. So this nozzle shall be big enough to avoid having flooding on the nozzle, and to facilitate the evacuation of condensates.
All right, thanks.
You're welcome. And the same for the non-condensables accumulation. It means the vent design, the vent nozzle shall be designed to facilitate the evacuation of the non-condensables. And another type of horizontal shell-side condensers are the TEMA X type. These types of exchangers are used when the pressure drop is a problem, is a concern. So usually they are used for vacuum condensers. In this case, the TEMA X type, it means that we have here only one shell side nozzle. This one is a distributor. So we have the inlet nozzle, a distributor of our vapor, which will be distributed along the shell side. And instead of having baffles, we have supports. So our vapor is not flowing along the tube bundle. Our vapor will be going down through our tube bundle. So that way, the velocity is very low compared with J-type or E-type. And since the velocity is very low, we also have a very low pressure drop, which is good for vacuum systems, vacuum condensers. In this picture, you can see here one nozzle only with this distributor. We can find also in industry not having the distributor, but having more than one shell site nozzle. So we can have here one nozzle, here another nozzle, and here another nozzle. And the same for the condensate. We can have more than one condensate outlet nozzle. Usually this is just an engineering rule of thumb, or when we have very, very large condensers, more than 6 meters tube length, we have 2 nozzles minimum for the vapor inlet, and usually we have 3. It means that with 3 shell site nozzles, we will have here 1, 2, and 3, and the vapor will flow down across our tube bundle, where it gets condensed and goes out with the bottom shell site outlet nozzle.
Olga, just a question. How do you control the vapor velocity? That, maybe if it's high enough that it will, blow through the condensate out?
Well, this is a parameter we have when we design the condensers or every heat exchanger, actually.
Yeah.
With we use the HRI program.
Yeah.
But if you are using HYSYS, for example, there is the part of HYSYS that designs heat exchangers is EVR, and with this program you can see the velocity on the shell site and also the pressure drop.
Okay.
Inside the shell site, actually, there are several different velocities. We have velocities, what we say, in the window. In the window, it means in the part where there is no baffle. And we also have velocities across the tube bundle and different angles. So velocity inside the shell site is just a prediction, but usually what the programs say is that it's just an approximation. It's not as effective as the velocity calculated for the tube site, because inside the shell site there are a lot of different parameters and a lot of different velocities in different angles. So it's just a medium number, a medium velocity, and an approximation. So we have this velocity, but the most important number is the pressure drop we have in the shell site.
All right. Okay. Thank you.
You're welcome. So the main advantage is this type of exchanger have the lowest pressure drop. This is why they are recommended for vacuum services. And as a disadvantage, the construction cost may be higher, considering required nozzles to obtain adequate flow distribution. So as I said, we can have here more than 1, 2, and 3 nozzles. So these have a cost impact in piping and nozzles. And also another disadvantage is the difficulty in removing non-condensables. In this case, we have this vapor inlet with a distributor here. And here in this sketch, it is not represented, but we will have here a small vent nozzle and also here a small vent nozzle. For example, if we have just 2 nozzles without having the distribution, we will have here 1 nozzle, here another nozzle, and we need to place also a vent nozzle. So this vent nozzle will be placed in the middle. Okay, so that's, yes, okay. And so now we have talked about the external condensers, where we have seen all different type of thema types, E, J, and X. And we have seen also the different configurations if they are located vertically or horizontally. Now we will pass through reflux condensers, but before, if you have any questions regarding this type of condensers, please just let me know.
شباب أحد عنده سؤال أو استفسار؟
لا استاذ احمد، بس السؤال اللي انت سالته، هاي الاندر سايز اوتلت نوزل، ما فهمت الجواب الصراحه.
هذا شنو اللي يصير؟ انت يعني هي ديسادفانتج شو يصير اذا النوزل الاوتلت مال كوندنسيت السايز مالت النوزل مو بيج انف، يعني مو الحجم مالتها مو كبيره بكفايه بحيث تحاول يخرج كل السائل المتجمع نتيجه الكوندنسيشن اوت. شو يصير فلودنج عندك، يبقى سائل بالاسفل الكوندنسر، هذا يعني ما محبذ، فلازم تتخلص منه. شلون تتخلص منه؟ تكبر السايز مال النوزل. افرض 10 انج اوكي، انت شو تسوي؟ تختار مثلا 12 انج. هذه من سويتها 12 انج راح يميك شور انه السايز يعني بيج انف انه كل السائل يطلع، بحيث ما يبقى سائل محجوز بداخل الكوندنسر. واضح؟
واضح. اشتي لك.
احد عنده سؤال او استفسار شباب؟
السلام عليكم.
السلام ورحمه الله على استاذ.
بس بلا زحمه تايب جي ليش كان مقسوم نصين بارتيشن all circle؟
Okay. Olga, and type J, why there was partition in the middle of the heat exchanger or condenser?
Yes.
Yeah.
In this case, we have baffles, and these baffles direct the fluid along the tube bundle. So, since here we have one inlet in this part and one inlet in this part, the fluid we have in this part is getting right direct to the middle, and same for this one. This fluid is being directed with the baffles and going down in the middle with the condensate out. So we have this partition because we have one velocity here and one velocity here. Usually it will be the same, but this shell side fluid and this shell side fluid shall not be mixed because they are already separated. So what we want is that the fluid goes down, the condensate goes down, and the non-condensables goes up. We do not want them that this fluid goes to this part. We want this fluid goes.
I think what will happen maybe because also the velocity, high velocity. So what will happen if you don't have this partition? You get a lot of the vapor goes through the excess vapor vent because it takes the easier path. So
also, yes.
So that's other reason. Let me check with the gentleman. استاذ واضحه لو اشرح لك اياها؟
والله اشرح لي اياها بلا زحمه.
استاذ عامر، هي شنو الفكره؟ اذا انت هذه ما موجوده، تخيل انه هاي ما موجوده، انت الفيبر راح يجيك من دني النوزلات على اليمين وعلى اليسار. دائما مثل ما قلت قبل شويه، الفيبر ياخذ الباث او الممرات الاسهل له. فشي يسوي؟ يطلع مكان ما انت تبدي تكثفه، ياخذ الطريق الاسهل، يطلع بالاكسس فيبر فنت. هاي واحده من المشاكل اذا ما عندك هذا البارتيشن. ثاني شيء البارتيشن تجبر الفيبر يسلك طريق معين بحيث انت تضمن اكثر عندك كميه كوندنسيشن تتكون خلال اجبار الطريق الفيبر الى يمر بخلال البندل تيوبس. تفهم قصدي؟
اوكي يعني فهمت قصدك، بس يعني كان نقدر ندخله مثلا من البدايه ونخليه يعبر على بارتيشنات ويطلع من النهايه. ليش يجي التقسيم هذا والتعقيد؟
مو قلت لك
يعني اكو فد
حكيت هذا النوزل ان والنوزل ان الواحد، مو انت فصلت الفيبر الان الى قسمين؟ اذا هذا ما موجود، اذا هذا ما موجود البارتيشن، ممكن انه الفيبر يطلع باتجاه وين؟
يعني يصعد للخارج.
بالضبط.
بس هو اكو بارتيشنات تنزله.
لا مو هذا انت سويت هسه كانما عندك اثنين مبادلات، خليت البارتيشن كانما اثنين مبادلات عندك.
هو سينقسم الى قسمين.
اي بهاي الطريقه راح تضمن الكوندنسيشن الكفاءه مالته اعلى.
اوكي.
تفهم قصدي؟ يعني هسه لو انت تتخيل ماكو هذا البارتيشن، قسم من الفيبر راح يطلع ويا البن، قسم منه ما راح يمر بالطرق اللي انت مرسومه له، بالنتيجه شو يصير؟ عندك كميه الكوندنسيشن تقل، فبالنتيجه
تقل الكفاءه.
تقل. بالضبط.
شكرا.
Any more questions شباب؟
لا استاذ، بس الاكس تايب الكولنت ان والكولنت اوت، شوف بي مالتي واي، ذهاب واياب هنا بس شنو الفرق؟ ليش هن كلهن مو نفس الشيء؟ لو هنا يعني
لا
شنو الفرق؟
نفس الفكره. هو انت شو تسوي؟ انت قدر الامكان تريد تسوي عمليه تكثيف، فانت من تزيد النمبر اوف باث، من تخلي الممرات تصعد يعني اب اند داون، فانت شنو بدك تجبر الفلو يتعرض للتبريد. فكل ما تعرض للتبريد اكثر سويت عمليه تكثيف اكثر، قللتهن راح تصير عمليه التكثيف اقل.
اوكي.
شباب احد عنده سؤال او استفسار؟ Okay, I think it's time to break, Olga. Yeah, 20 minutes.
Okay.
Or long. أستاذ عدي تردون 20 دقيقة لو أكثر.
اوكي استاذ احمد، هاي براحتك.
20 minutes.
هسه 10 ونص نرجع. ماشي.
Okay, half past 10 or half past 12 in Iraq time. Okay.
Okay.
Yeah. So half we come back 30 past. Yeah. Thanks.
Okay, good. Thank you.
Okay, guys, I think we are back now. So I think, Olga, you can resume the presentation. Thanks.
Okay, thank you, Amit. Okay, just up to now we have done the external condensers. And the next one we are going to explain are the reflux condensers. In this kind of condensers, the reflux condensation is the process in which vapor flows upward past a cold surface and condenses, forming a liquid that flows down counter to the vapor flow. We will see now some sketch, but before, in industry, reflux condensation is often used to remove condensable components from non-condensable gases being vented. It is also used in some types of distillation column condensers, in which the condenser bundle is inserted directly into the column top to save piping. And there are two different main types of reflux condensers: the tube side condensers and the shell side condensers. And are these two types what we are gonna see now. You're gonna start with the tube condensers. Several geometry types are possible for reflux condensers, although the most frequently used is the vertical tube site. Vapor enters the bottom header and flows up through the tube's counter to a liquid film of condensate on the tube walls, which drains back into the inlet header. Excess vapor escapes into the exit header at the top and flows out, the excess vapor and the non-condensable gas. In this case, cooling water enters at the top of the shell and exits at the bottom. So as you can see in this image, this okay, so I was saying that the vapor enters through the middle of the tube and condensate forms a film in the tube wall that flows down. Avoiding flooding at the tube inlet is very important, and this is the reason that the end of the tubes are cut with an angle of 45 degrees approximately. So with the tubes cut that way, it enhances avoiding flooding at the tube inlet. And this configuration for reflux condensation has potential benefits of increased separation of light and heavy components. So this is for the tube side condensers, but we also have the shell side condensers. They are sometimes specified because designers normally prefer to place cooling water on the tube side of the condenser, especially if the water is likely to fall, like cooling water. Also, for vacuum distillation, shell side reflux condensers can be placed directly above the column to minimize pressure drop. Different geometries are possible for shell side column top condensers. We will see the vertical column top shell side condenser. We will see also the vertical step-in column top shell side condenser. The horizontal column top shell side condenser. And the horizontal step-in column top shell side condenser. So in the following slides, we are gonna see these 4 different types of shell side condensers. It means that always the coolant service, for example, cooling water, will be placed inside the tubes, and the fluid that we want to condense is placed on the shell side. So let's gonna start with the first one, the shell side condenser, the vertical column top. Vapor on the shell side must flow counter to the draining condensate to reach the cold surface. The maximum upflow vapor velocity must not inhibit the liquid draining process and cause the liquid back up in the condenser. It means flooding. The upper portion of the condenser, beyond the point at which most condensation has taken place, often is fitted with baffles to increase velocity and improve performance. So as you can see in the picture, we have the vertical column top condenser with baffles on the shell side, which allow us to increase velocity, also enhance the separation between liquid and vapor, and the vapor goes up while the liquid also goes down on the same part of the shell side. Another type of shell side condenser is the vertical step-in column top. So it means that the condenser is inserted inside the column. These condensers are not true reflux condensers because vapor can enter at the top and around the sides of the vandal. However, they work as a reflux condenser. The U-tube bundle is inserted vertically into the top of a distillation column that replaces the condenser shell. Fluid circulating in the tube side shall be clean. It means that usually this type of configuration with cooling water, we have to ensure that this cooling water is very, very clean because we are using U-tubes. And as we said, with U-tubes, it is not easy to clean inside the tubes. So all the fluid located inside the tubes shall be clean. Vapor flowing up from the top tray condenses on the shell side, and liquid flowing back down provides column reflux. Excess vapor exits via vapor vent nozzle located below the tube sheet. Okay, so we have seen the vertical shell side condenser, the one mounted on top of the column, and the other one inserted inside the column. Now we are gonna see the horizontal condensers. This first one, the horizontal column top condenser, which is placed on the top of the column. So shell side reflux condensers are preferred when tube side coolant is cooling water or another fluid which is likely to fall as a horizontal condenser with a cooling water placed inside the tubes. It is easy to pull out not to pull out, it is easy to open this part and to clean the inside of the tubes than with a vertical condenser type. So with fold fluids as the coolant, we prefer horizontal condensers. The maximum upflow vapor velocity must not inhibit the liquid drain process and cause the liquid to back up in the condenser, floating. So the velocity here shall be lower than the liquid going back. So then we have to avoid here having the flooding. The upper part of the upper portion of the condenser, beyond the point at which most condensation has taken place, often is fitted with baffles to increase velocity and improve performance. So here in the sketch they are not drawn, but we have here baffles also to increase velocity and heat transfer coefficient. And finally, we have the horizontal step-in column top. So these are placed horizontally. Usually, this configuration is chosen when the fluid circulating in the tube site is likely too full, since it is easier to clean. And when it is located vertically, it is mandatory to use U-tubes, so tube site cleaning is not accessible, or is less accessible than in this case. In this case, there is not mandatory to have U-tubes. We can have an M thema type, but in this case, we need to have U-tubes. This condenser is not true reflux condenser because vapor can enter at the top and around the sides of the bundle. However, as for the vertical condenser, it works as a reflux condenser. Sorry. So in this case, this type of condenser has also very low cost because we do not have a true shell site because the bundle is inserted inside the column. So what we only need to consider is to have enough space in the column to place our condenser. As we see in the reboilers, we have also a step-in reboilers. So in the column, what we have to consider and to take in mind that we need to have enough space to place our condenser. Now we're gonna see what we need to consider to select the right condenser. But before, if you have any question regarding this last part of the types, please just let me know.
Guys, do you have any questions?
النوع الاخير يعني هسه كانه ماكو شغله هنا يعني هو
مو هي بداخل
ما
تحتاج شغل.
هو الشغل
ما تحتاجه.
اوكي.
Really good. Olga, just a question. I haven't seen or come across, you know, such of type of reflex condenser in the oil and gas or refining industry. So what are the applications for those type of reflex condenser, which is either inserted or mounted on the top of the tower?
Well, to place these, to have this type of reflux condensers, we use them usually for vacuum distillation processes where we need to have a very low pressure drop, because having this type of condensers, we do not have these piping pressure losses. So maybe not this one, but this one, just let me know. This one is very, very common in the industry. Also, it is located on the top, but it can be also located here on the side.
Yeah.
So this inlet nozzle is located here. So this will be placed on this pad. Just maybe I can, yes, I think I can. Okay. The nozzle will be located in this part. And we can have a nozzle in this pad. So we place the inlet nozzle, the inlet on the shell side, we place it here.
Yeah.
And we avoid having pressure losses on the pipe. So for vacuum systems, this is very, very common. Also this one is less likely because usually the coolant system is cooling water, and as I said, we do not like having cooling water with U-tubes. So it's only used when the duty, the heat exchange is very, very low. We can place the condenser inside the diameter of our column. It means that we need to have enough diameter to place our condenser, and the coolant service shall be clean. So this is, since usually the coolant is cooling water, this is not very common. And this one is, as I said, this is very, very similar to this one. This is used when we do not want to increase the column length. So we just mount the condenser in a column, and here we have some reinforcers to place our condenser on top of the column. But with this type of configuration, we do not need to increase the column length.
Yeah. Okay, but obviously that's only pure reflex you have. You have no product coming up. Okay.
Exactly. Yes.
All right. Thanks. I've got a question. I think.
You're welcome.
Mr. Ramir, yes.
السلام عليكم استاذ احمد.
ورحمة الله على الأستاذ أمير. أهلا وسهلا.
استاذ ولو زحمه، اذا يعني هاي كل نوعيه اكو منع موجود عندها في مصفى كربلاء بس، ولو التاج نمبر مالتها يعني سهوله المتابعه مالتها.
هسه راح نجي لهذا.
ما صور عليها وكذا.
راح نجي لهذا الموضوع. هسه يعني.
اوكي اشكرك استاذ.
Any more questions?
استاذ احمد، بالنسبه للتيوب باندل بالفيرتيكال كولون توب، هذه بنهايتها اكو يصير هدر، مو صحيح؟
هدر؟
يعني حتى يرجع الكولنت شلون؟ يعني باليوتيوب واضح شلون يرجع الكولنت، زين بالفيرتيكال كولون توب الكولنت شلون جاي يطب ويطلع يعني؟
هو انت بالتيوب يطب ويطلع، بالتيوب يطلع من الجهه الثانيه.
يعني اكو فد انابيب نازله اللي تحت سلايد 49.
Sorry, Olga, can you show me 49, please?
Yes. Yes.
Thanks.
هنا الكولنت يعني يدخل الاسفل ويرجع، يعني نهايه التيوبات اكو، اذا مو يوتيوب يعني اكو هدر شلون؟
لا هسه التيوبات هاي جايه منها، هسه هذا الكولنت ان صح؟ دخل
نعم.
هي ما موجوده التيوبس، ما تشوفها انت هسه التيوبس.
اقصد يعني اذا اكو تيوب بنهايتها اكو، اذا مو يوتيوب اكو هدر.
لا مو هذا مغطى، شوف هذا الهيد، الداشت هيد هذا اللي بالاخير. مو انت ما تقدر يعني، هاي مو بروبر داتا شيت حتى يعني اقدر انا يعني اوضح لك، تفهم قصدي؟ بس هو اقصد
يعني هو المقارنه، اذا اكو يوتيوب مو صحيح، هذا اليوتيوب اللي يوتيوب واضح هسه يدخل ويطلع يعني بكل.
هو استاذ يوتيوب استاذ حبيبي، هو يوتيوب بس هاي عندك ظاهر بس الشيء.
اي ماكو
يوتيوب واضح ورا من ورا.
هم يوتيوب يعني.
هم يوتيوب، هو دائما يوتيوب.
Guys, this YouTube type here, the tube side.
تمام. زين هاي الفقره البافل تو انكريز فيلوسيتي اند امبروف بيرفورمانس، يعني هاي ممكن يعني توضيحها شلون يعني انه البافل يزيد
Olga, so we've got two questions. I want you to answer them. So this type of tube side, this is YouTube, right?
Yes, it shall be YouTube because it enters this way.
Yeah, and then turn.
And then turn and goes up.
Okay. That's one question. The second question, how this buffles will increase the velocity and you know the improve the performance. So if you just give a bit more clarification about this paragraph.
Yes, the baffles, actually the main use of the baffles in this exchanger, but also in all the exchangers, no matter if they are vertical or horizontal, is to force the liquid to pass through the tube bundle. So since they are forcing the liquid or vapor, they increase the velocity. Otherwise, imagine if there is no bundle, no baffles, sorry, this just go up like this with no forcing to move the fluid, so then the velocity is lower. With the baffles, we redirect our fluid, we increase the velocity, we force the velocity. So these increase our heat transfer coefficient. Increasing the velocity means increase the heat transfer coefficient.
Yeah, thanks. استاذ مرتضى.
واضح استاذ احمد، بس عندنا نقطه يعني هنا هو صار تعرج يعني الليكويد اللي الفيبر اللي صاعد بهاي الحاله يقل سرعته لو يزيد.
لا مو انت ايش راح يصير عندك؟ مو سبيس مفتوح، انت من قصرت او قللت خلينا نقول القطر، تخيله مثل الانبوب، من قللته بالنتيجه السرعه راح تزيد.
انه هذا البفل يعني صار يعني مسارات اكثر، فبالتالي زادت الكفاءه هنا، بس هي ما زادت السرعه، بالعكس يعني انا من اقلل السرعه ازيد زمن التعرض ما بين يعني الفيبر والكولنت، مو صح هيك؟ فبالتالي
لا السرعه شلون تزيدها؟ انت مو قلت لك لو تتخيلها مثل البايب مثلا. هسه انا اسالك سؤال، السرعه بالبايب ابو 12 انش نفس السرعه ابو 8 انش؟
يعني الضغط يزداد صار.
صح، بس وياك استاذ احمد، بس هنا السرعه المقصوده هي بالكولنت، كلامك صحيح، بس اذا سرعه مقصوده
لا تحكي عن الليكويد، اذا تحكي عن الليكويد
على الليكويد يعني هو صار بي يعني مثل ما نقول تعرجات، فبالتالي يعني مو اصور يعني هي قلت السرعه، بالتالي زاد زي من الكونتاكت تايم ما بين الليكويد
لا مو انت نفس الشيء، هو الفيبر او الليكويد اذا انت يعني قللت القطر الممر مالتك شو يصير بالسرعه؟ انا اذا سالتك هذا السؤال ما جاوبتني اياه.
اذا قللت القطر تزيد السرعه. ليش؟
زي نفس الشيء، هو غير نفس المبدا. يعني هسه انت مثل هذا الشل افرض مثلا متر القطر مالته، اذا سويته نص متر شو السرعه ايش راح يصير بها؟
لا صحيح وياك انا اوكي متفق، بس هو هنا الكلام مو انه قللنا او زيدنا القطر.
لا انت سؤالك تقول ليش تزيد السرعه بالبفلز موجوده. البفلز دا اقول لك انت تسوي عندك تخصرات بالفلو، التخصرات
واضح تمام واضح فكره.
قلت لك تخيله كانما انبوب، يعني انبوب اذا 8 انش نفسه ابو 12 انش، لا طبعا لو هذا مفتوح السرعه تصير اقل، يعني ولو ما
شكرا استاذ ممنون.
يعني استاذ احمد هي تزيد السرعه وتزود زمن البقاء نفس الوقت.
وانت من زادت السرعه سويت، من زادت السرعه راح يمر على الممرات يعني الممرات اللي بالتيوبس اكثر. اذا السرعه بطيئه شو يصير؟ راح يصير ياخذ جهه من دون جهه ثانيه. تفهم قصدي؟ يعني افرض كله يتركز بالجهه الايمن الاسهل له مما يروح يمنى ويسرى، فبالنتيجه اصلا كفاءه التكثيف تروح تقل يعني كثير. بس هي هاي الممرات تساعد انه تجبر عملية التكثيف او التبادل الحراري اكثر. ليش؟ لانه تزيد عملية السيرفس اريا تتعرض لها الموائع اكثر، يعني هذا المبدأ يعني. اوكي شباب، احد عنده سؤال او استفسار؟ شباب يعني الحاضر 95 واحد، او خلينا نقول 90 متدرب، يعني اللي يسألون بس 3 أو 4.
استاذ واضح ان شاء الله، واضحات
ان شاء الله. اوكي Olga, sorry, you can carry on. Yeah, thanks.
Okay, thank you. Okay. Okay. So when identifying and designing a condenser, several aspects shall be considered. The first one, we take a look to the allowable pressure drop we have. So selecting the correct condenser will make that pressure drop is well distributed along the exchanger. Limiting the pressure drop is a key design goal for condensers. And to have a good allowable pressure drop, we need to select the adequate thema type. So for condensers, where allowable pressure drop is very limited, thema type will be X type. However, if allowable pressure drop is not a constraint, it can be selected the E type. Here on the right, we have divided the different thema types according to the pressure drop we have. So the E and G shell is the exchangers we will select when thema type, when pressure drop is not a constraint. However, if we want to decrease as much as possible the pressure drop, we will select another type of thema that decreases the pressure drop as H and J shell, or the last one, the X shell. This one is the thema type with the lowest pressure drop. So usually for vacuum condensers, we use X shell. The second aspect we consider is the coolant process constraints. If coolant is likely to full, it will determine if vertical or horizontal condenser will be selected or if U-tubes can be used. Also, the condensing fluid process constraints. Select the adequate condenser type to adapt to the condensing service in case there are non-condensables or it is a mixture or there are heavy components. For example, we consider having close-spaced baffle to improve the vapor phase coefficient for mixtures and non-condensable fluids. And the last point, the last but not least, we'll say, we have to consider the metallurgical constraints. Select the fluid allocation depending on the materials. Usually, the fluid with special material needs, as noble materials, are located inside the tubes. That way, it is not necessary to build the shell side also in that noble material. So for all the fluids that they need special materials, they will be allocated inside the tubes. So this are the 4 major aspects we consider when selecting the right condenser. If someone has any question regarding this, because now the next slide will be to see some examples at Carvala Refinery. So this is the last slide for the condensers module. Just let me see if you have any question.
واحد عنده سؤال؟ Okay, you can proceed, Olga. Thanks.
Okay. So the last point of this session will be to see 2 examples of heat exchangers, 1 reboiler and 1 condenser at the Carvala Refinery. As for the heat exchangers, these pictures are random heat exchangers at the Carvala Refinery. So I have chosen the same unit that we saw in the heat exchangers session, the unit 3 isomerization unit, where we find the deioninizer column. The purpose of this column is to recover product isoxane and pentynes from the stabilized Penex reactor products. The deioninizer column separates the stabilizer bottoms into 3 streams. The net overhead liquid, where we can find it here at the bottom of the column, going out in vapor phase and condensed in air cooler. Sorry, the bottom. Okay. Yes, this one. I said the bottom, but it's in the top. So the net overhead liquid, where we can find it here at the top of the column going out in vapor phase, and is condensed in this air cooler. We also have the side draw liquid. This stream is the one we saw in the heat exchangers session, where the side draw liquid is this one, was cooled down with an air cooler first and a shell and tube after. And we have the net bottoms, where the desioxanizer column is reboiled by the desioxanizer reboiler with medium pressure steam. So the first exchanger we are gonna see is a desioxanizer reboiler, a shell and tube heat exchanger. And the second exchanger we are gonna see is a desioxanizer condenser, is an air cooler. So for the reboiler, here you can see the sketch with the column, and the reboiler is a BXU horizontal reboiler. We are gonna take a look first to the datasheet. Just this usually should work. Now, okay. So we have the mechanical datasheet with the process specification. First, we have one part where it is specified the thema type. Here we can see we can select between B, we have B type, and also then we can choose between E, G, and H or G. And also we have U tubes. It is an horizontal thermosiphon. And why is that selected? Because let's gonna take a look to the duty. We have around 20 megawatts. So we can see we can say it will be located horizontal since duty is very, very high. So then we will need to have very long tubes. So it is better to place long tubes in a horizontal way than a vertical, configuration. To have a good configuration and to avoid as much as possible to increase the height of the column. We have the hydrocarbons placed on the shell side and the heating medium, the MP steam, on the tube side. We need to vaporize 30%. And then we have here construction per shell. These are standards that the engineering are standards, but then these details will be specified during the reboiler design. Also, the data sheet considers specify the properties at 3 different enthalpy curves. This pressure covers all the range of pressure that there is between the column and the reboiler. So it is important to specify 3 different pressures, the properties of 3 different pressures that covers all the range between the column and the exchanger. And what else do we have of information? We have to take a look also to the heat exchange to the falling resistance. We see that on the shell side, the fluid is very fouling. So we will want a design that allow us to clean the shell side easily. Okay, so this is the configuration. We have the column this way. The shell and tube, the reboiler is placed horizontal. And then with this configuration, since we are working in a thermosiphon way, which means that we need to have a liquid static head that allows our fluid flow from the column to the reboiler and back again to the column. We have the exchanger will be designed at normal liquid level, with it is located at 910 millimeters from the tangent line. We have X type with 2 shell side inlet and 2 shell side outlet to locate better the pressure drop. And with vapor on the tube side. In this page, it is specified the reboiler design. So we will have a reboiler with a shell diameter of 1,400 and 7.3 meters tube length. And the surface is 602 meters square. So this is a very, very big reboiler. We have square tube arrangement, which allow us to clean better the shell side. So as we said, the fouling factor is high on the shell side. So we try to have the best arrangement to allow cleaning the tube bundle. So this is the sketch that we are gonna see with the mechanical drawing. And this is the tube bundle. As you can see, we have a square tube pitch. We also have an impeachment plate because the velocity is high at inlet and we need to protect the first tube row under the shell nozzle. Okay, so I think there is nothing else to point out of this information. Yes. So now let's gonna take a look to the mechanical drawing. Actually, the main point that for me that I was surprised when I opened this process data sheet is the duty. For me, that was a very, very big duty. So with this duty, you automatically go for horizontal thermosiphon because it is better to place and to have the thermosiphon effect and to decrease the liquid static head. Imagine if you have these 7 meters of tube, because here the tubes are located horizontal, but imagine if you have this horizontal exchanger located vertically. This distance would be much more higher. So then we will need to increase this height much more than what it is increased with horizontal shell. So this is the main point that I want to point out with this thermosiphon reboiler. Okay. So now we are gonna see the mechanical drawing. Okay. So as you can see here, we have a B head. And in the shell, we have X type with 2 shell side nozzle inlet and 2 shell side outlet nozzle. And we have U tubes. since we have MP steam, we have steam is a clean fluid, and we have condensing clean fluid inside the tubes. It is better. So in this case, we have supports instead of baffles. So it means that the fluid, it is not redirected with the baffles, because the fluid, it enters and goes up. It is not redirected. So baffles redirects the fluid, supports only support the tubes. We see here we have the impeachment baffle. And in the next page, we have the detail of the baffle, of the supports. Are these type of supports cutted like this, that they cover all the tube bundle. So all the tubes are supported by these supports. We have the impeachment plate located here, and enough space here to allow having a good velocity, velocity at inlet. The square type to allow cleaning on the shell side. Okay. And this is a detail of the impeachment baffle, square impeachment baffle. Sometimes they can also be rounded, but usually they are squared. And that would be all for the reboiler, for the thermosiphon reboiler. If someone has any question regarding the thermosiphon reboiler, please just let me know.
We've got just one question here. I think question says more likely fouling fluid should be located in the tube side. This is the rule, yeah? So why for one of this reboiler, the rule is reversed? So they put the more fouling
yes.
fluid on the shell side.
Yes, in this case, let me go for the process data sheet. Okay, we have a huge amount of liquid that we are vaporizing, and the pressure drop is very low. So we need to place the hydrocarbon on the shell side, because we need to decrease as much as possible the pressure drop. If we place the hydrocarbon on the tube side, the pressure drop will increase a lot, and we cannot do it actually. This is why it is used, this thema type with two shell side nozzles to split the fluid and to decrease the pressure drop.
Yeah, so there are priorities when you select. It's not just only fouling, and that's the override criteria. No, the pressure drop is more important than
Exactly. In this case, we have a process constraint, which is the pressure drop. So then it means we are adapting the thermosiphon to the process requirement, that is the pressure drop. So it doesn't mean that we cannot, having this process constraint, it doesn't mean that we say, no, it is better for the design of the thermosiphon that the most full fluid goes inside the tubes. No, because we can work with it and we can place the full fluid on the shell side, but what we are saying is, okay, we are placing the full fluid on the shell side, but I am gonna let my exchanger ready for maintenance. It means that my exchanger is easily to clean. I can clean the shell side because I have U tubes and the bundle can be extracted, and I select to have square layout, which facilitates the cleaning, actually. So I am adapting my design to the process constraint that is the pressure drop.
Thanks, Olga. شباب أحد عنده سؤال أو استفسار؟
تمام رحم الله والديك.
Okay. Thanks, Olga. Thanks so much for your presentation, and thanks everyone for attending the session. We'll see you.
Well, actually, we still have the last example, the air cooler. If you have time.
Yeah, sure. Go ahead.
Yes. Okay. Okay, this is the last example I want to do of this column. Is the condenser that we will find at the top of the column. So let's gonna take a look to the mechanical data sheet with the process considerations. Okay. First of all, we consider there is a huge heat exchange, 22 megawatts. So it's a total condenser. We have a huge amount of liquid that we condense, and we have a forced air cooler. This is a very big air cooler with 10 bays, and the tube length is very big, it's 9.5. So it is also specified the air conditions, the temperature in and after the design. The air outlet temperature is 67.7. So about the air cooler design, we have 10 bays, and in each bay we have 2 tube bundles. So it means that we will have 20 tube bundles in parallel. This air cooler is located on the pipe rack with ladders, walkways, and platforms. The tube length is 9.5, is a standard number. We have extruded fins. We have 2 fans per bay with very large fan diameter. And we also, we want to control the airflow with an auto variable pitch. It means that the blades can move. And this is the power of our air cooler per bay. These are the properties of our fluid at 3 different pressures. Okay. And here I just wanted to point out that the note that it says that air cooler to be self-draining, meaning slope for last pass. Let's gonna take a quick look to the general arrangement, to the mechanical drawing. If the presentation wants to to show us the drawing. Yes. This is the mechanical drawing, and this is the view of our air cooler from the top. We have here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 bays. Each bay has 2 bundles. I have colored here in 2 different colors. This is one bay, and in each bay we have 1 bundle and another 1 bundle. And each bundle has 2 nozzles, and this one 2 other nozzles. And this bay share, in the bay, the 2 bundles share the fans. So, okay, this is the view of the air cooler from the side. We can see here we have two rows, 1 row, 1, 2, 3, 4, 5, 6, 7, and 8. And we have 2 tube passes. If you remember in the presentation, I said that for air cooler condensers, the last part of the air cooler shall be sloped. So this is how it is sloped. This part is separated, and this second pass is sloped from this one. And as you can see here, here you can see that this second part is sloped 10 millimeters per meter, only the last part and the second part. So this is the inlet, the process inlet, where the vapor enters. It is condensed in this header, goes back with the second part of the tube bundle, and it goes down the condensate. We need more tube rows on the first pass, because the inlet is 100% vapor, and the pressure drop in this part is higher. In the second pass, it's mostly liquid, so it is enough having only 2 tube rows regarding the pressure drop. This is the drawing of the header, how we see the header from the side. With different views and different details of the mechanical partition, the mechanical, how they are sealed and everything. But what I wanted to point out mostly here was this sloped to be let it in the air cooler condensers. So that's okay. That's all for the condensers. That's all for the reboiler and condenser online session. Please also tell me if you have any question.
Thanks, Olga. شباب أحد عنده سؤال أو استفسار قبل ما ننهي السيشن؟
شكرا جزيلا أستاذ.
Okay, thanks. Thanks, Olga. Thank you so much. Really
شكرا جزيلا أستاذ.